think it's time. So you've seen most of this slide before. I just want to mention first, if you look at the blackboard, you can see that answers to the test, the math test, are available, so you can check. And if you have any questions, discuss those questions in office hours. All right. Backup is ready. Now, of course, I know many of you are concerned about exams, and as you know, because I told it, exam problems are similar to homework problems, lab problems, class problems, or combination of those. And the best way to practice in recognizing those similarities is practice, because practice makes results. And you know the saying, you can bring horse to water, but you can't make her drink. So there's plenty of water for you, and you're much smarter than any horse. So use that information. This is what we've finished for now. Everything about one-dimensional motion. Trajectory is a straight line. Vertical, horizontal, or tilted, doesn't really matter. And we can use coordinates, specially measured numbers, to represent instantaneous. It sounds too loud to me, no? No? Maybe it's just this spot. Okay, so numbers which represent instantaneous position and how it changes in time. We can use graph or motion diagram to demonstrate how it moves. And we know the displacement, which is an arrow in general, but for a one-dimensional motion, it is equal to just difference between final position and initial position of an object. And if we know distance or displacement and time, we can calculate things like average speed or average velocity. So this is a question I want to ask you right now. Two problems are on the screen. Number one and number two. The question is, do you think these problems are different or the same? The one on the top, it was the last problem we started yesterday, and we'll finish it today. But before we go to straightforward calculations, I want to see what you think. A similar question could be asked about a person. If you look at that person, well, from behind and from a side, is the same person. Because what you see, clearly different. Yeah? So what is actually a difference? Just out of curiosity, check if WebAssign is working. So 26. So if you look at the appearance, yeah, you can see some difference, and that difference is one problem has a specific number, another problem instead of that number, uses a letter. Well, does it matter? No. Because when we need to solve a problem, we have to follow a procedure, a process, a sequence of steps. And those steps don't matter, don't depend on, for those steps, you know, if we have some numbers assigned to some variables or don't, that doesn't matter. The steps, the strategy doesn't depend on a specific information inside the problem. So it's like choosing the origin relative to what? Yeah? Relative to sheer appearance, they look kind of different, like the same person viewed from different views. Yeah? Look differently, of course, but it is the same person. So it is the same problem. It requires exactly the same strategy, exactly the same reasoning, exactly the same process. But, of course, when we have numbers, it just makes us feel easier. But remember, from lecture number 1, feelings in physics don't matter. So let's go through this problem in general. It doesn't matter if we know or don't know something, because it's we, it's us, humans. Universe, nature doesn't care about us. It works on its own, whether we exist or not. And this fly would fly exactly the same way whether we existed or not. So numbers, not for universe, for us. But we need to know how to understand the universe in general. So of course we use the standard approach. We need to visualize what we started. So visualizing means drawing a picture. So, well, I don't have to draw a fly. Yeah, I can draw anything, because again, it doesn't affect the phenomenon, the process. Still, travels west, and well, that's the first part of this trip. So, a certain amount of time required to travel, certain distance, L1 b meters, and that's it. Now it makes a U-turn, and then it travels back. We don't know, so it doesn't really matter. Doesn't affect the general strategy. Is it's longer, shorter? So this portion of a trip requires a different amount of seconds, and the length of this portion of the trip is different. So those variables which we extract from the text, however, we know, because we have a hint here, this hint, average velocity. An average velocity, according to a definition, that's the first thought which should pop up in our mind, according to the definition, is equal to so what is it equal to? Please tell me someone, I forgot. And you don't know if I lie or not. I might forget. Yes? Displacement over time, exactly. And this is a one-dimensional motion, so we can choose axis along the path. And of course, technically, no one tells us to point positive direction to the right or to the left. It's up to us. But everybody points it to the right. So positive numbers go to the right. And displacement will be equal to this, delta XO, which is final minus initial, and delta T is the time to make that displacement. Now, this axis missing the origin. Well, this is just a ruler. Yeah. A ruler. number line. Again, nature doesn't have number lines. Nature doesn't have rulers. Nature doesn't need rulers. People need rulers. We want to be ruled, right? And sometimes, when we have to choose a ruler, we're stuck with egoistic narcissistic or orange egoistic narcissistic. Scratch that. So, origin, where? Because nature doesn't care, we choose it anywhere we like. So, let's choose it. Well, normally, it's the initial location, final location, or the most left location. Those are most convenient choices. And in this situation, so we can choose the origin here, at the initial location. We can choose it here at the final location, or we can choose it here at the most left. The most left is convenient because it makes all x's positive, because they all will be to the right to it. How do you choose it? Up to you. Doesn't matter. So where do you want to choose it? Okay, thanks. So now, relative to this choice of the origin, our initial x will be equal to this length, L1, or number b. Our final x will be equal to L2, or that distance d. And this, like, x middle, or x west, yeah, because that's a point of the return where it happened. This x will be equal to 0 because of our choice. And now, this situation has 3 individual parts. Yeah? Well, we can discuss the motion to the left, the motion to the right, and the whole motion, which means we can apply this equation, the same equation, 3 times. First time we can apply it to the motion due west, second time to the motion due east, third time to the total trip. The same equation, but when we apply that equation, of course, we will have to use specific numbers or variables related to those quantities. So there should be some average velocity on its way to the left, and that should be equal to, so according to our, well, okay, x final 1 minus x initial 1 over delta t 1, and that's got to be x final 1, that's 0. X initial 1, that's just x initial, which is L1 or B, and time was A. That's it. Now that equation describes average velocity, and as we know, velocity and speed are different in some properties. For example, speed, which is distance over time, cannot be negative, because distance cannot be negative, but velocity can, and this average velocity actually is negative because it points to the left, opposite to positive x direction. We can draw a short arrow which represents that velocity, points to the left. Now we can write an equation, well, it has some magnitude, maybe given, maybe we'll be looking for that, it doesn't matter. Now, for the second part of the trip, the average velocity, which should be positive because it points to the right, should be equal to, well, again, final for the second part minus initial for the second part divided by time of the second part. In our variables, that's going to be d minus 0 over L2. See, the same point, 0, origin, has different meanings depending on what part of a trip is considered. For the first part, that's the final location, but for the second part, that's the initial. And for the total trip, total, that should be equal to, again, x final for the total minus x initial for the total over time over total. Well, x final relative to our origin for the total equals L2. X initial equals L1. Total time, of course, will be equal to first plus second. So it's going to be A. Oh, why? Why? And no one said anything. At least you should be asking, why? I don't know why. I said sometimes one thing and write another. It happens. So that was C seconds, C. So, and going to be A plus C. And that's going to be negative because essentially it moved to the left. So this is the average velocity for the total trip. Points to the left, got to be negative. But of course, you can easily eliminate all negatives by using absolute values. And then you can plug in all the numbers you want, and you can solve this problem. And this is the place where you could do it, or I could do it, but I won't. That's homework 1, part 1, problem 3. So this is when and where I, at least, like to say. Physics is done. When physics is done, only then, finally, what begins?
Try to put in absolute values. Like the only thing absolute values do is just change the velocity from negative.
You don't have to use it. I said if you want to. It's completely up to you. Mathematically, it's absolutely irrelevant. But some people just don't like negative numbers.
Absolute values, do you have to say, like...
You have to keep track? No. If you use absolute values, you have to keep track of differences. These differences, if you use them correctly, automatically give you positive result or negative result. But if you want to use the absolute value, in that case, you need to think how to make this positive. Anyway, this is the abstract question. The actual question arises when you actually start doing it. And when you start doing it, in that case, maybe you will not have any questions. So, we've talked about difference between velocity and speed. For velocity, we use displacement. For speed, we use distance. Now we need to talk about difference between average and instantaneous. Average tells us something about the whole trip. It neglects all details of the trip. Just initial, final, what was happening in between, we don't know, we don't care. But of course, we also need to know what is happening here and now, at this very instant. And to do that, we need to measure or calculate instantaneous variables. And this is a standard definition of what this word instantaneous means. It means that we just considering two instances very close to each other, or two locations. so close to each other that we actually cannot differentiate them. Maybe our powerful software can, but we cannot. So for us, 1 second and 1.001 seconds, practically same instant. So instantaneous basically means average over a tiny time interval. That's it. When an object almost didn't move. That's an official definition. Now, instantaneous speed defined slightly differently than average speed. It's not defined through length, no. By definition, instantaneous speed is just the magnitude of instantaneous velocity. So if we know instantaneous velocity, which could be positive or negative, absolute value of that, that's what instantaneous speed is. And when people say those words, speed, velocity, they automatically mean instantaneous. Only when they want to describe average, they add that word, average. So when you read speed, velocity, it's meant instantaneous speed, instantaneous velocity. So when you drive, what do you think? What device do you think can you use to to know how fast it's happening? So every car has a speedometer. It gives you a number. Now we know many numbers, yeah? We know average speed, average velocity, instantaneous speed, instantaneous velocity, distance, position. So the speedometer, of course, shows only one specific number. Which is that? So that's your question. These are possible answers. So go to web design, select, click, submit, and please tell me what you think. Instantaneous speed, that's not a tricky question, of course. It measures speed, so you can cross out answers with a different word, velocity. And of course, it measures it here and now. So if you drive to measure, you use speedometer to measure your instantaneous speed. And when a policeman catches you, that's what policeman also measures, your instantaneous speed. But if you want to know your average speed, in that case, you got to use odometer to measure how many miles did you travel, and watch to measure total time, and that's it. And none of these devices provide any information about direction. For that, you would need a different compass, for example. So if we talk about one-dimensional motion, this is how we calculate average velocity. This is how we define instantaneous velocity. But we never use this expression. So in a second, you can just erase it from your memory. Because this is the algebra-based course, and this is a calculus. Instead, we're going to use a different approach. So this is, again, a definition of instantaneous speed, which is magnitude of instantaneous velocity. We can use graphs to extract information about average velocity, instantaneous velocity. So let's say some object is traveling, and graph for position as a function of time, I don't know, like a cart running down the track. So if we pick two different instances, 1, 2. So at this instant, location was at x1. At this instant, location was x2. So if you want to calculate the average delta x over delta t. That's what we got. x2 minus x1 over t2 minus t1. Now, the British alphabet has only 26 letters. Physics has hundreds of variables. So very often you have to use the same letters for different things. And when you do that, you have to know what you use it for, and you have to be able to say out loud the exact meaning of the exact letter you're using. Because the same letter T, for example, might mean an interval, how much passed over the time, or an instant. In this situation, that's an instant. This T, it's an instant, but this is the interval, delta T. And this difference actually will be equal to the length of this segment of a number line. And this difference, x, and so this is delta T, this is delta x. And if we calculate this ratio, in mathematics we call it rise over run. And rise over run is equal to what? Slope of this line, or the tangent of this angle. So this is the meaning of the average velocity. We can draw a line through 2 points, and the slope of that line, or the tangent of that angle, is equal to this average velocity. Now what we're going to do, we're going to make instant number 2 get closer and closer and closer to the instant number 1. So it's not here anymore. Let's say it's here. So the new location will be here. And the new line will be slightly different. And we can try it again and again. And of course, now it's really hard to see what's going to happen. But that's where we have to turn on to the full our imagination. That's why imagination is more important than math and physics. We would see something like this. A graph. 2 points which we cannot distinguish because they're so close to each other. So for us, identical, simultaneous, and a line which touches this graph at only 1 point. And how do we call this line? Tangent or tangential. And of course, the slope of this line will be equal to the instantaneous velocity at this instant, at that location. Instantaneous velocity. That's how we always can get the value for instantaneous velocity. Now, of course, we can immediately refresh our knowledge about slopes. A slope can be positive, a slope can be negative, a slope can be 0, like velocity can. And well, this slide just represents the summary of everything I just said. So question, please. So when object was traveling, making one-dimensional motion, this is not a trajectory. The trajectory is a straight line, but an object might have been traveling left and right along that line. And we can use this graph to actually draw a motion diagram to see how the object was moving. But for now, we need to use this graph to answer the question about point F. At point F, the velocity and I'm going to draw, well, sketch a motion diagram. So a motion diagram shows how the object was moving along the x-axis. So it starts from point A, which is above, I don't know, 0 or whatever, doesn't really matter. And then, oh, where is it? And then actually it travels, well, if we write it 0, that's not 0. It's getting closer and closer to 0. So it's going to travel to the left. At point C, it actually stops. And then it starts traveling to the right. And then at point E, it stops again. And then it starts traveling to the left. Well, point G, and then H, etc., etc. That's the motion diagram. That's the trajectory made of different horizontal segments. And my analysis also helped to answer this question, because if at point F the object was moving to the left, that means velocity is what? Negative, yeah. Or we could draw a tangent line, look at it, we see the slope is negative. Technically, to measure angles, we would have to measure angle from positive x direction toward the line. And if we want to, we can calculate the tangent of this angle. Because angle is above 90, it will be negative number automatically. So, any questions? So, what does negative mean? Again, if we draw a diagram, it means velocity points opposite to positive x direction. That's what it means. Well, if it's not velocity, if it's something else, it always means the same thing. Could be negative force, negative acceleration, anything which is a direction. Still means points opposite to positive x direction. Now, a special case of motion with constant velocity. It's a one-dimensional motion when object travels same distance in same time in same direction. But mathematically, the easiest way to describe it is by stating that there is no difference between calculating average velocity or instantaneous. It's always the same. You can take 1 second interval, 0.1 second interval, 10-year interval, and calculate velocities, you get the same number. That's what constant means. And if the velocity is constant, means the slope of the graph is constant. So the graph for position as a function of time should be a straight line. Well, not necessarily up, could be horizontal, could be down, but it must be a straight line. Now from mathematics, we remember the equation which describes a straight line is a linear. The relationship between dependable and independent variable should be linear. So this is a motion equation for the one-dimensional motion with constant acceleration. That's it. If time equals 0, this is what we call y-intercept. Yeah? If time equals 0, this coefficient gives initial location x0. And if we calculate the slope, that is the slope. So this coefficient represents velocity. Which velocity? Instantaneous or average? They're the same, so just velocity. And this is how we write this equation in physics. We start from initial location, and then the term which describes how position changes. When velocity positive, the graph goes up, object travels to the right. When velocity is negative, the graph goes down, object travels to the left. When velocity is 0, nothing is happening, the object is at rest. So technically, rest is a special case of the motion with constant velocity when it remains constant and remains to be 0. Now let's practice a little. So we have a graph for the position as a function of time. It has 3 parts, and the first thing to do is to draw motion diagram. Let's do it right here. So to draw a motion diagram, first we should draw the x-axis. choose the origin. And what we see is 1, 2, 3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So that's 7. For 3 seconds, it was traveling to the right until it reached 7 meters. And call it V1. What was happening between t equals 3 and t equals 18? The x coordinate remained the same. So it wasn't even moving. It was resting right here. And then for 5 more seconds, it was traveling back. So V2, 0, V3 will be negative. So this is the trajectory, basically. That's it, motion diagram. Now, equations. Motion 1, motion 2, motion 3. For the motion 2, this is the equation immediately. 7. It's 7, 7, 7, 7, 7, 7, 7, 7, 7. That's between t equals 3 and t equals 18. So that's done. That's simple. And that's what you should do when you expect that different parts of a different problem might be more or less difficult. You should start from the easiest one. And on the exam, you also should start not from the first problem and go to the last. You should start from the easiest and go to the hardest. So now the next part is so that's for number 2 part. That's for number 1 part. We know that it's a linear motion, so should initial plus velocity times time should be linear, and the equation should be linear. What do we know? We know initial 0, and we need velocity, and we can just use this pair of points. It's supposed to be equal to 7/3. So the motion equation, 0 plus 7/3 times time, or just, and that equation works for time between 0 and 3 seconds. That's it. So now the last part, right? So that's the initial. That's the final locations for the last part. So the equation, still standard equation, linear equation for the motion with constant velocity. So now we need to use the graph to extract the information we can. Initial x for this motion is 18, and someone said something, I heard it. Was a question? Ask a question. Yes? Oh, I look at the time. Yes, sorry. 7. Thanks. Thank you. I was already looking at the time. Now, thanks. See, morning. Deficiency of coffee. And now we need velocity. And that's supposed to be, well, first of all, it has to be negative, right? But your instinct tells you to do this, 7/5. Because what you see here and here, and that would be wrong, right? So there are 2 ways to fix it. First of all, we can say this is the magnitude, but the actual value is supposed to be negative, so just add a negative sign. Or you can just literally follow the definition. So it should be equal to 0 minus 7 divided by 23 minus 18. That's automatically, wherever it is, 7. And the equation is x equals 7 minus 7 over 5 times time. That's the motion equation for the third part of the motion. Same equation, but it has to be applied to each individual part of the graph. Any questions? Yes?
Why do you write it like the x and the y-intercept would be partway through the graph and not from the actual axis?
I don't understand the question. Which y-intercept? First of all, which part of the graph do you refer?
You write 7 plus, why do you assume it's 7 and not where it would actually meet the y-axis?
Which part of the calculation you talk about, this or this? Because the reasoning behind these calculations is different.
Why do you write the
This?
exponential to be 7 instead of where it actually meets the intercept?
This? This?
You write xi as 7, but y is partway through the graph.
Like, why is the initial position?
This? First I want to understand, the question is about this or something else?
Yeah.
This, perfect. So, x changes. How? This is where, again, it's very handy to have a motion diagram, because that's what you look at. This is a graph, a mathematical abstract, which represents how x changes in time. The actual location zero, 1, 2, 3, 4, 5, 6, 7. The actual location was at x equals 7, and it started moving from here, and because it starts moving, the word starts makes it initial. And from here, it moved back to 0, 0. And that's the final for the third part of the trip. Did I answer? Okay. Please. So I'm going to switch pretty soon. Please take a mental picture and choose your answer. Switching. So that was question number 5. We still have 52. I'm going to wait for 30 more seconds. There are two approaches. Number 1, using a definition of what you're looking for. Number 2, using a common sense. Using a common sense means eliminating answers which don't make any sense. And out of 6 answers, 5 don't make any sense. For example, it cannot be negative because it doesn't go beyond the initial location. And it don't exist. It exists because it always exists. It's always some number, positive, negative, or 0. And those 7 over 23, 23 over 7, absolutely random kind of ratios. But of course, in order to be absolutely convinced, you would have to use a definition, and the average velocity is delta x over delta t. And this equation can be applied individually to each part of the motion or to the whole trip. And for the whole trip, it's going to be 0 minus 0 over 23. Because it starts at 0 and it ends at 0. So the answer is 0, right? Okay, when velocity changes, first of all, terminology. When we use these words, speeding up or slowing down, we don't talk about velocity. We talk about the speed. Speed is never negative. Speed is a positive number. That positive number might increase or decrease. And if speed increases, we call it speeding up. If speed decreases, we call it slowing down. Now, when speed changes, or object speeding up or slowing down, and this is a very common model to keep in mind how it might happen. Speeding up, slowing down. So when speed changes, we need something to characterize how fast velocity changes, because velocity is more important than speed. Velocity also has a direction. And of course, when something changes, we calculate rate of change of that thing. And this is an official definition of new variable which describes how fast velocity changes. We call it, well, in this situation, average acceleration. Final velocity minus initial velocity over time. And so let's say it rolls down. Because it's a very common situation, we can use our common sense, and we can choose 2 locations, x initial, x final. Let's say, even to make our life easier, initial speed is 0. It starts from rest, but here it will be moving, and we know how. It will be moving down the ramp, and that will be some positive number. So if we want to calculate average acceleration, it will be some positive number divided by, well, some time, positive. Acceleration also has a direction, and in this situation, it points in the same direction as x-axis, in the same direction as velocity. That's always the case when an object speeding up, velocity and acceleration point in the same direction. Slowing down. So this is our initial position. And let's say we gave it a push. So initial velocity points up the ramp. First of all, it makes it negative. And we can, again, to make things easier, we can assume it stops right here for the moment. So final velocity is 0. So average acceleration, average, should be final minus initial over time. Now, please tell me, average acceleration, if we calculate it like this for one-dimensional motion, it is a number, and any number only has 3 choices: positive, 0, negative. So if we finish this calculation, what number do you think we get? Positive, 0, or negative? Okay, if you think negative, please raise your left hand. If you think positive, please raise your left hand. All right, let's make another simplification. We said this number, initial velocity should be negative, right? Please pick and tell me any negative number. Well, we can't say 5. Negative 5 meters per second. That's a negative number. Now we can use a negative number to calculate average acceleration. 0 because of this, minus because of this. Now negative 5 because of this divided by time. So is it positive, 0, or negative? Positive. It's all there. Minus 1, this is an invisible 1, times a negative number makes it positive, still positive. What does it mean? It means acceleration will be directed as the axis in the positive x direction. But relative to velocity, it will be opposite. See? That's always a case for slowing down. Velocity and acceleration opposite to each other. Always when object slows down. So, any questions? That's what it means about the mutual direction. Speeding up, velocity and acceleration point in the same direction. Acceleration helps to move it faster and faster. Slowing down means acceleration, which people call deceleration. Don't do that, it's wrong. It's outdated. It's still acceleration, but it points opposite to velocity. That's why velocity decreases. Speed decreases. So, of course, we have only a finite number of combinations. This slide shows all possible combinations. Velocity may be positive or negative, acceleration may be positive or negative. So, positive velocity, positive acceleration, positive velocity, negative acceleration, negative velocity, positive acceleration, negative velocity, negative acceleration. That's it, done. All possible options. And some of those options give you result we call speeding up. When both are positive or both are negative, because they point in the same direction. And some of these options give you a case which we call slowing down when one is positive and one is negative because they point opposite to each other. That's it. Here, let's say picture C. This car, speeding up or slowing down? Slowing down because acceleration and velocity are opposite. What about B? Slowing down. A, speeding up. D, speeding up. In A and D, car speeds up, but in case A, it speeds up and travels to the right. In this situation, it speeds up and travels to the left, but faster and faster. Please take a minute. The real question, did he hit it? And what happened next? So, I see that some students think and some students do. And you know, thinking is wrong, doing is right. Doing means you have to take a pen, draw a picture, east, west, and the guy was traveling west. That was velocity. Before applies the brakes and we call initial. And suddenly, deer comes up. And what's happening? Is the driver speeding up or slowing down? Slowing down. You have to say it in words. And that just your common sense. But now, after having said that, you know that velocity and acceleration must be each other. So this is basically not a physics question. This is a fill in the blank question. You just have to fill the blank correctly. What should you write here? Opposite. What's opposite to left? And how do we call this? That's it. Well, for the acceleration, also, we use difference between average and instantaneous, but the meaning of instantaneous acceleration is exactly the same as instantaneous velocity. We just have to calculate average acceleration over a tiny time interval, and the result will be exactly the same if we have a graph for velocity as a function of time. The tangent line represents how fast velocity changes here and now. The slope of that line is equal to instantaneous acceleration. Exactly the same reasoning, exactly the same idea. But of course, we're only going to talk about specific case when instantaneous acceleration and the average acceleration are equal to each other, the same, so we don't even distinguish them. We just say acceleration. And in that situation, if acceleration remains constant, that means the slope of the graph, velocity as a function of time, remains constant. The slope, velocity, time. The slope remains constant means this graph has to be a straight line. So for velocity equation, we also have to write a linear equation which relates velocity and time. And the linear equation, well, has always one constant, independent variable. This is the slope. But now, this slope has a different meaning. That's acceleration of an object. That's the initial velocity when time equals 0. That's all left. And in this example, the slope is positive, acceleration is positive, but it could be 0. Motion with no acceleration is a special case of motion with constant acceleration. When acceleration remains constant, 0. And there's negative. So these are options. But of course, we need to figure out how to describe the position. And in physics, we have several approaches to do that. We can do calculus, we can do geometry, or we can do experiments. And that's what you do in this course. Half of you already have done it yesterday. Another half we'll do it today. We do experiments, and we extract the information for that experiment, which tells us how to relate the velocity equation, which must be linear by definition. This is how we write it in mathematics. This is how we write the same equation in physics. We start from initial velocity and acceleration times time. This is our goal. And to do that, we take a track, place a cart on it, run experiments again and again and again and again, and based on that set of experiments, prove, not algebraically, not theoretically, practically, that for the motion with constant acceleration, motion equations should be quadratic. Graphs should be parabolic. We cannot change it. It comes from experiments. So again, in mathematics, a quadratic equation looks like this. It's a standard way mathematician writes a quadratic equation. In physics, we write the same equation backwards. We start from constant term, second quadratic. And if time equals 0, what's left? This. So this constant represents the initial location. This coefficient represents initial velocity, same number. And turns out this coefficient is related to acceleration. It is not acceleration, but it is related to the acceleration in a very simple manner. Now, when we have that information, we can use that information because now we know everything about motion with constant acceleration. This is another representation of the same equations. Now, I advise you to do just to practice your algebra skills, to do it at home. So these are standard equations for motion with constant acceleration. Velocity equation, motion equation, also called position equation. You look at this equation, it doesn't have time in it. What did you do? Well, you do algebra. Two equations. You solve one equation for time, plug it in this, do algebra simplifying. That's the result. Of course, you don't have to do that. You can just memorize this equation and use it when you want it. A second convenient equation. We know that by definition, average velocity equals displacement over time. But in a special case of motion with constant acceleration, we can prove mathematically. Again, this is a physics class, so I'm not going to do that. But you can, for the sake of practice, you can prove mathematically that average velocity also equals mathematical average, initial velocity plus final velocity over 2, which is also handy. So it's up to you. You can believe it, and that's it, or you can doubt and prove it mathematically. So this is what we've learned. We have several types of motion. Well, first of all, nothing is moving, rest. The position graph, horizontal line. Motion with constant velocity, position graph is a straight line. Motion with constant acceleration, the position graph is a parabola. And we can use many combinations of those. So we've learned everything. Of course, now we just need to practice. Let's say we are given a specific motion equation, like this one. And we just need to extract all information we can. Well, first of all, I always rearrange terms according to standard form of the motion equation. First, a constant, then a linear term, and then a quadratic term, right? And this equation is supposed to be absolutely identical to standard equation for motion with constant acceleration. So now, if you look at these two equations, this is a general equation for motion with constant acceleration. This is a specific. Forgot. Specific, yeah. Equation for motion with constant acceleration. Specific, of course, supposed to have exactly the same form as a general, but with specific values. Which values? Well, initial position for that specific motion is equal to a specific number, which is what? 6. Well, unless we told otherwise, we automatically assume we are using international system of units, so 6 meters. What about initial velocity? Please tell me. Anybody? Just scream. 24. Yeah, if we look at this. Well, technically, this is what we should have been writing. 24 times time equals initial velocity times time. That's what makes them equivalent. We can cancel time here and there. The answer is 24 meters per second. Now we can move on. Please tell me. I got it blue. Number which represents acceleration of that specific motion. Louder, please. Negative 12, I've heard, and I heard 6. 6, negative 12. If you think, so that's a, when we have a disagreement, it's a democracy, we have to vote, right? So if you think the answer is 6, please raise your hand. Well, you said it, you have to raise your hand. Or if you think it's negative 12, please raise your hand. Democracy wins. Okay. Meters per second squared. Well, of course, technically, that's what we should have done. So we have to compare these two terms. Negative 6 times time squared should be equal to 1/2 a time squared. And done. And now, of course, we can calculate anything we want to. But it's much more interesting to understand what is happening. The best approach is sketch a graph. Here, our knowledge of math might be handy. It's a parabola. So we have two types of parabolas. And the type depends on the quadratic term. This is for a positive coefficient. This is for a negative coefficient. So this is a negative coefficient. So we should see a graph like this. And what does it mean? It means that an object initially travels from, well, 6 meters away from the origin, 6, but it stops at a certain point, so it reaches some maximum location. And then it returns and travels back. So this could have been used as a motion diagram. It travels here, returns, and travels back. Of course, it would be nice to find how far did it travel before it returns. Well, this is a very special location. What is happening at the object at that location? That way it stops. That's, try to find simple answers. Because normally in physics, you always can find a very simple answer in 1 or 2 words. It stops. It stops here, instantaneously. which means instantaneous velocity here becomes equal to 0 for the fraction of a moment. Well, if it's velocity, we need the velocity equation. Velocity equation, no problem. Velocity equation, we know, is initial velocity plus acceleration times time. In our specific situation, that's initial velocity 24 and acceleration negative 12. That's it. That's our equation. And the graph for velocity as a function of time according to this equation looks like this. Starts from 24, goes down, 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 goes through 0, becomes negative. This is the same instant, t middle, I don't know, t middle. How do we find it? Well, we know that at this instant, velocity becomes 0. That's what we know. We just have to finish the equation and solve it for that instant. And that instant will be equal to 2 seconds. And now we can calculate this position. That's maximum to the right. It should be equal to 6 plus 24 times 2 seconds minus 6 times 2 squared. What's happening after? Well, after it travels back, and if time keeps running infinitely, so eventually it goes through the origin and flies away to the left. But faster and faster and faster, because after that, it's speeding up. So this part, when it travels slower and slower and slower, see, this, how does slope changes? Steep, not so steep, no slope. So velocity decreases to 0, slower and slower, but after that, it travels faster and faster and faster and faster. This is an illustration how equations, graphs, motion diagrams, and everything what's happening related to each other. Any questions? All right, that is just an example of a specific problem. An object was initially at rest, and then it was brought to a motion, was traveling at constant acceleration, and how much time would have to pass until the speed is 15 meters per second. If the magnitude of that acceleration equals 5 meters per second squared. All right. So, of course, picture worth 1,000 words. So, positive x direction. Let's call it origin. Let's call it initial. Doesn't really matter. And we made it move to the left. The velocity, which changes also, but still, after an initial instant, always points to the left. And acceleration points to the left. It moves faster and faster, so they have to point in the same direction. The magnitude of acceleration is 15 meters per second. And no, that's a velocity. 5 meters per second. And the speed, the final speed it needs to have, and speed is the magnitude of velocity, 15 meters per second, bless you. Of course, it also travels a certain distance, L, it takes a certain time. At this point, you have a choice to make. Wrong choice is to think, what do I find We don't care. That will come later. We're not looking for certain specific, no. The right choice is how to describe this situation. How to describe this situation? Well, that depends on the situation. This is a situation which has a specific name, motion with constant acceleration. What do we know about motion with constant acceleration? Well, at least two fundamental equations. Velocity equation and the motion equation. Done. Now, how can we use these equations? Well, that depends on the information given to us. For example, V initial, it has to have magnitude of 15, but it's negative, so that's the initial value of, final. That's the final. V initial is 0 because it begins from rest. Acceleration. The magnitude is 5, but it points to the left, so the actual value negative 5 meters per second squared. Well, that's already sufficient because we can now use the velocity equation. If we can't use an equation, we have to use that equation. And using means plugging numbers in that equation. So negative 15 equals 0 plus negative 5 times time. And then solving that equation, time equals 3 seconds. And we're not asked for anything else, but of course now we also can calculate the distance traveled, but because distance is related to position, we would have to use the position equation. For example, if we plug in numbers, x final will be equal to 0 plus 0 times 3 plus 1/2 times negative 5, 3 squared over 2. That gives the final coordinate. But if we know initial, which is 0, final, which is this, we can calculate distance traveled between these 2 points. And this type of strategy works for any problem on motion with constant acceleration. Don't think what I know, what I need to know, what I'm looking for. That's never going to help you. Think how to describe this case. And that will eventually lead you to what you want to find. One more problem. The airplane lands. When it lands, when it touches the ground, touchdown, the speed is 70 meters per second. When it slows down to 10 meters per second, it travels 500 meters. And, well, find everything, basically. So, after having read this, what do? Draw a picture. And if I do that, and I've been doing it for years, that means you have to do that too. And if you don't do that, that means you don't follow in my instructions. And if you don't follow in my instructions, why should I help you? So draw a picture. Oops. Wrong direction. Wrong direction. So x-axis. Well, here. Landing point, set origin at the landing point. That makes initial velocity to be 70 meters per second. And after traveling for 500 meters, the velocity becomes equal to 10 meters per second. So distance traveled will be equal to, in my situation, that final velocity, 500 meters. Anyway, first we have to make a statement about the nature of this situation. And the nature of situation is motion with constant acceleration. So what do we know about motion with constant acceleration? When short answer, everything. Longer answer, the velocity equation and the motion equation. Okay. These are generic, general equations for any motion with constant acceleration, and we need to apply them to this specific situation. And what does make this specific? Well, certain numbers, for example, 10 should be equal to 70 plus acceleration times time. When I know a number, I have to use it. Using means plugging it into the right spot. And what else do we know? Well, we know the location, final location, initial location, plus initial velocity was 70 and 1/2. Do we know acceleration? So when I know a number, I write a number. When I don't know a number, I just have to write a letter which represents that number. I have to imagine that I know it and proceed in a way I would be acting if I knew it. And I have to believe that it is solvable. I have to believe I can do that, because if I don't believe, I give up. And if I give up, I don't succeed. Now let's look at this. What do we see? We see this. One equation, two unknowns, doesn't work. We see this. One equation, two unknowns, doesn't work. But if we look at them together, what do we see? Two equations, two unknowns. That's what we call a system. So at this point, I'm done. As a physics course, physics is done, I'm done. What begins? And that's on you. But there is a shortcut, which I want to demonstrate to you in the last, yes?
How did he know that it had a constant acceleration?
Well, first of all, there is a word acceleration here, and that's assumed, because if it's not constant, this problem would not be solvable. There are many assumptions which implied in all problems. And those assumptions are natural. Like those assumptions should make the situation simpler, solvable, workable. When velocity changes in this course, it only changes with constant rate. So a shortcut. There was an additional equation on the screen. So we have a motion, we have a velocity equation. We have a motion equation, that's velocity. But there is also a third equation which has no name. And that's the name of that equation, the equation which has no name. Which has been proved mathematically from these two. By eliminating time, doing some algebra. And in this equation, if we use our numbers, this is 10, This is 70. Well, this is a 2. This is acceleration, but that was 500. And this equation, of course, can be immediately solved with the acceleration. And you, of course, will get a negative number because it was slowing down from 70 to 10. So negative means acceleration should have been directed away from the positive. That's acceleration. So it should have been negative, and it will be negative. Let's see what else we have. Okay. I'm not sure about you. I can solve it in 1 minute. A small ball was released from a window. Well, all previous problem implied that the motion was horizontal, but we know one-dimensional motion doesn't have to be horizontal. If I let a ball fall, it will be falling down along a straight line. One-dimensional motion, that's it. So we can apply everything we've learned about horizontal motion to this motion. So the building is 49 meters above the ground, and the time to hit the ground was equal to 1 second. Now, the initial velocity of this ball equals what number? 0. How do we know? No. It says released. We'll let it go. Yeah? How do we know it's released? How do we know the ball was released? Anybody? It's on the screen. But more importantly, because we can read. If we couldn't read, we wouldn't be doing this problem. So there's a reason for everything. That's 0. That's all my time. Yeah, I know. All right, so of course I'll finish it tomorrow, but technically you know everything already to finish it. Yes. What do you have?
Combination letter?
Oh, okay. It's about